Hello everyone, welcome to all of you in my YouTube channel. Today is the second lecture, lecture 2 of the rotational dynamics. Uh, rotational dynamics, rotational dynamics. This is the lecture 2, lecture 2. So in the lecture 1, basically we studied some basics of the, like, what is the rigid body, what is the properties of the rigid body, what exactly is the moment of inertia, and we already calculated the moment of inertia of the thin rod about the axis of rotation which is passing through the center, and about the axis of rotation which is passing through the end. In today's lecture, first I will define the radius of gyration. Radius of gyration. Radius of gyration is basically represented by K. So, what is radius of gyration? So, suppose we have any body, okay? Suppose we have any body, and this body is rotating about some axis, okay? Let's say this body is rotating about this axis with some angular velocity, that may be anything, okay? So every body has certain mass, certain point at which whole mass of the body is supposed to be concentrated, and that we also called as a center of mass also. It is a point, let's say that it is a point at which whole mass of the body is supposed to be concentrated, okay? I just represent it or denote it as cm. So this distance, the distance from the axis of rotation to the center of mass, the perpendicular distance, actually the perpendicular distance from the axis of rotation to a point at which whole mass of the body is supposed to be concentrated is called the radius of gyration. So let us define this, let us write this, how actually we can write this. The perpendicular distance, the perpendicular distance from axis of rotation, from axis of rotation, the perpendicular distance from axis of rotation to a point at which whole mass of a body, at which whole mass of a body is supposed to be concentrated, okay, supposed to be concentrated. So this is the formal definition of the radius of gyration, and mathematically we just write moment of inertia of any body in terms of the radius of gyration as m times k square, okay, m k square. So where this m represents the total mass of the body, m represents the total mass of a body, okay, m represents the total mass of a body, and k represents the radius of gyration, and I is the moment of inertia. So sometimes in exam you may ask, like, what is the radius of gyration for the thin rod or something else. Okay, for that we actually, how we can calculate like that. For example, for thin rod, okay, for thin rod, generally for the axis of rotation, when axis of rotation passing through the center, we actually have I is equal to mn square divided by 2n, okay. So what we can do is that, suppose if we write this as equation 1 and it as equation 2, we can just equate it. We can equating equation 1 and 2. Then what we will get? in the left hand side there is I, but in the right hand side here mk square and here ml square over 2n. So will be cancelled out, and k will be L divided by root over 2n. Okay, root over 2n. So similarly, when the axis of rotation, when this is the moment of inertia of the thin rod when the axis of rotation is passing through the center. So sometimes the axis of rotation may be passing through the end also. So in such cases, what we will do? Okay, in such case also we can also find, like for axis of rotation, axis of rotation passing through end, okay, passing through end. For which case? For the thin rod. Okay, for the thin rod. In this case we have moment of inertia as ml square by 3. Then again we will do the same process where we will equate them. So after equating, okay, we will get this mk square, and this is ml square over 3. Again m will be cancelled, and k is equal to L over root 3. Okay, this one. So, and one thing that you have to remember is that solid sphere, okay, in case of solid sphere, I is equal to 2 by 5 mr square, where r is the radius of that solid sphere. So basically we are not required to derive this relation. We just have to remember this, because this may asked in some numerical problems or in some conceptual questions also. So here also for the solid sphere also we can calculate. Similarly, as we done before, like mk square is equal to what? 2 by 5 mr square. Okay, so here again m cancelled, and k is equal to root over 2 by 5 times r. So this is the process how actually we can find the radius of gyration for any body. Okay, so this is what I actually want to highlight over here. Now I just move to the another topic. Okay, let us move to the another topic, and that is torque. Okay, let us move to the another topic, and that is torque. What exactly is the torque mean? So torque is basically a force which actually turns the body. Okay, it is actually, in simple words, it is also called as turning effect of force. Okay, torque is generally turning effect of force. Basically it is the force by virtue of which the body will turns, the body will rotate. So there can be many examples. For example, we have the door. We are just applying the force, and by virtue of which the door rotates. Okay, similarly we are opening the tap. Okay, we are opening the tap, we are opening the cap of a bottle. There can be so many examples where actually we are dealing about the turning effect. Okay, so this is the turning effect of force. So it is also called as moment of force. This is also called as moment of force. Okay, so that means tau is equal to F times R. So where F means applied force, okay, this is force, applied force, okay, and this R is distance from axis of rotation, okay. Actually torque is the vector quantity. So in vectorical terms, it is generally written as tau is equal to r cross f. In vector form, it is written as, sometimes you may be asked in the examination also whether the torque is scalar quantity or it is the vector quantity or something like that. So in such cases, torque tau is equal to r cross f. We will write that. And okay, so this is the definition of the torque, and we should also know about the unit. Unit means obviously you can clearly see over here. This is Newton force. This is tau is equal to F into R into F, whatever you call it. Force, unit of the force is Newton, and this is meter. Okay, so it is simply with the force. Okay, it is the force in the rotational motion. Simply you can understand that it is the force. It is the force in rotational motion. Okay, it is the force in the rotational motion. Okay, or we can say that in case of translational, in the translational motion, the role played by force, and here in case of the rotational dynamics, the same role is worked by the torque. So it is the force equivalent we can say. Otherwise you may got confused how it is different from force like that. So like for example, you can here, for example, in translational motion there is force, and in rotational motion there is torque. So in this way you should have to understand it is the force equivalent in the rotational dynamics. So I have already stated that there are many examples. Okay, especially so many cases. For example, there is one question also, why the range that we used to open the screw or like that. So why it has the longer arm. Basically, for example, we have some range like this. Okay, if the length is longer, or sometimes like this also, this is also sometimes range. Okay, if the length is large, if the arm length is large, obviously the distance from the axis of rotation will be increases, and by this relation tau is equal to rf. Here, even if we apply the same force, but the distance is large, if we use the range of the longer length, okay, if we have the range of the longer length, the distance r from the axis of rotation will be large, and by virtue of which torque will be large. Although the force is small, but the turning effect that is produces on the body will be large. So in this way there are many possibilities, many different examples of the torque. You can explore those examples from the books or from the other parts. Okay, so let us now derive the relation actually. Relation between torque and moment of inertia. Okay, torque and moment of inertia. Okay, so let us derive this relation in a very short way. I am not going to in a very detailed way. I just skip the language part and I just focus on the mathematical portion only. For example, for this, let us we have any body. Okay, I have just taken any irregular body. Suppose this body is rotating about this axis with any particular angular velocity. So suppose this body has large number of particles, n particles. Okay, suppose I have chosen here m1, here m2, here somewhere here m3, or whatever it may be arbitrarily. Okay, and this distance is r1, this distance is r2. Okay, this distance is r3, and there can be many possibilities for the other particles also. So to find the relation between torque and the inertia, moment of inertia, what actually we can do is that when this body is rotating about like this, for this particle, For this particle, it actually inscribe a kind of the circular path. Okay, if we look at to the motion of m1, this path will be the circular. So here for mass m1, we will just for mass m1, okay, if I able to find the torque for the mass m1, then what I can do is that I can just add the torque for the other masses also, and then just add it. So for this, for mass m1, so what will be the torque? Tau 1 is equal to, earlier we have written the formula r1 f1 here in this case, because we are considering the mass m1, so I have written in the suffix here. So tau 1 is equal to r1 f1, so tau 1 is equal to r1 f1 in place of the f1 m1 a1, because the force is equal to ma. Okay, so acceleration, what will be the value of the acceleration in case of the rotational motion? I just show over here. Okay, I just show over here. So basically we have one relation, v equal to omega r. Okay, v equal to omega r is the relation which connect the velocity. This is the translational velocity and this is the angular velocity. If we differentiate this relation, if we take the derivative of this relation, this becomes dv by dt, and this will be d omega by dt times r. dv by dt means a, this d omega by dt means alpha times r. So a is equal to alpha times r. So here also tau is equal to r1 m1, in place of a1 we can just write alpha instead of alpha 1. Alpha 1, alpha 2 we will not write that, because the alpha angular acceleration remains same. That's why we just write alpha times r1, not alpha 1 r1. Keep it in the mind. Okay, so then tau 1 is equal to what happened, m1 r1 square times alpha. So similarly now you can say that what will be the torque for the another mass. Then what will be the torque for the another mass? Tau 2 will be m2 r2 square alpha. Similarly tau 3 will be m3 r3 square alpha. Similarly for the nth particle, mn rn square times alpha. Okay, so in this way actually we can find the moment of inertia, torque for the different masses. Now what to find the total torque? Okay, to find the total torque, tau will be tau 1 plus tau 2 plus plus tau n. This way I can actually add this. Okay, then what I get, tau is equal to, in place of tau 1 m1 r1 square. So you can clearly see that every terms there is alpha which is common. So I just write like this, m1 r1 square plus m2 r2 square plus plus mn rn square times alpha, because alpha is common over there in the all terms. So here tau is equal to this relation I can just write in the form of the summation, where summation I range from 1 to n mi ri square times alpha. You can, because for example in this case, if we vary the value of I, first we will write I is equal to 1 m1 r1 square plus then m2 r2 square m3 r3 square, similarly so on. So then this is the relation, summation mi ri square is the relation of the moment of inertia. Okay, this represents moment of inertia, and there is already alpha over there, so no worries on that. So tau is equal to I alpha. Okay, so this is the relation, tau is equal to I alpha. It is the relation that actually we want to find, that actually we want to derive over here between this torque and the moment of inertia. So okay, so which is exactly similar to the F equal to ma. In case of the translational motion, we have the relation F equal to ma, and in case of rotational motion, in place of F we have torque, in place of mass we have moment of inertia. In place of acceleration, we have angular acceleration. So that's why, just similar to the F equal to ma, but here in case of the rotational dynamics, some notations are changed. Okay, so after this I just move to another topic. Okay, now I just move to the angular momentum. Angular momentum. Angular momentum, it is represented by L. Okay, like the linear momentum, generally in the class 11 there is one famous principle also, principle of conservation of linear momentum. Likewise here also we have the principle of conservation of angular momentum. But before that, it is necessary for us to understand what exactly is the angular momentum. Then it would be easier for us to to understand that principle also. So angular momentum means simply it is the momentum, simply it is also be the momentum of the body when the body is in the rotational motion. Okay, so but in defining, it is defined as like it is the moment of linear momentum. Moment of linear momentum. It is the moment of linear momentum. Moment, how actually we can find moment? For example, just before I write down that moment of force is equal to F into I. So moment, something's moment means we just multiply that particular quantity with distance actually. So here in this case, L is equal to, it means P times R. Moment, why moment? Moment means because this is multiplied by distance R. Actually it is the perpendicular distance from the axis of rotation. P times R. P is the linear momentum, moment of linear momentum. L is equal to, it is defined, it is the moment of linear momentum. Okay, so here this is the linear momentum. So its relation, we know that linear momentum is equal to m into v, we all know that, and this is r. So L is equal to m times v times r is the relation. Okay, so its unit, you can just simply find its unit also. So I just like to establish the relation again. Okay, relation between this angular momentum. Okay, relation between this angular momentum and moment of inertia. Moment of inertia. By the same process that I have done before in case of the torque. So here also, suppose I am taking one body where it is the axis of rotation. I just do not want to go into the detail. Suppose this mass is m1 and this distance is r1. Likewise there is mass m2, there is mass m3, and so on. Okay, so basically here also we will find the angular momentum for m1, for the m1 only, m1, then we can generalize for the others also. So here for mass m1, how actually we can write? For mass m1, okay, for mass m1, so linear momentum, angular momentum L is equal to m1 v1 r1, because we have just before we have written the relation L is equal to m into v into r. So we have the relation, one relation, v equal to omega times r. So in this case we can just write m1 in place of v1, which it is we will not write omega 1 r1, but instead we just write omega times r1 times r1, because omega is the angular velocity and angular velocity is same for each particle. It is same for every particle. Okay, then what we will get? M1 L1 is equal to M1 R1 square omega. Okay, similarly for others, like L2 is equal to M2 R2 square times omega. Similarly for nth particle, Mn Rn square times omega. Okay, similarly for the nth particle. So just like before that we have done for the torque, here also total angular momentum. Okay, total angular momentum. Total angular momentum will be L is equal to L1 plus L2 dot plus Ln. So here also omega will be the common, okay, from the all terms. So L is equal to M1 R1 square M2 R2 square dot plus Mn Rn square times omega. Okay, because omega is same, omega is actually common to the all terms. So here L is equal to, we can just write it in the summation form. I range from 1 to n mi ri square times omega. Okay, so L is equal to, this term is actually I and this is omega, because this just represents the total moment of inertia and this one. So L is equal to I times omega is the relation between the angular momentum and the moment of inertia. It is very much similar to the general formula. In the translational motion we generally have linear momentum is equal to mass into velocity. Here in place of linear momentum we have the angular momentum. In place of mass we have moment of inertia. In place of velocity, here we have the angular velocity. So this is the relation. So thank you very much for today. In the next lecture I will continue the other parts also. So thank you very much.